Right, so today's webinar is on reliability testing, and one of the things I wanted to mention is, and to talk about, and it's something I'm sure I've mentioned in the past, is that testing is expensive, and getting the samples is always a challenge, and the ability to gather information from a poorly constructed test is in some cases less than useful. And so the question I have for you is it always necessary? Do we always need to do testing? All right. And looks like, Sean, you were able to download the slides. Great. So I'm going to suggest, Luis, if you could just give it a shot again. If not, then we'll be in touch, and you can let me know. We can get it to you another way, and we'll make sure that happens. Also, I'll have the recording, the slides, and the also a podcast version of this will be available probably this evening as I get the recording edited and posted. So, one of the questions that we often receive, and let me know if you've heard this question or not in your line of work, is concerning a product development, or you're working on something, you're putting in some new equipment, and somebody asks you, is it good enough? Are we there yet? Kind of idea. This is not an uncommon question that we face. And it's one of those things that we have a huge range of different tools available for us to try to answer that question. And of course, testing is one of those methods. Yet, are we making the right choices is a question that you may or may not receive when it comes to the work we do as reliability professionals. In this sense, I'm talking about, are we choosing the right vendor? Are we choosing the right materials? Are we choosing the right design approach, or the right concepts? Is this design going to work, is the previous question. In this one, there's so many decisions that are being made during the development process that the question invariably comes up to, is that the right choice concerning reliability? And then we also get questions, especially near the end of a program, are we sure? Is the evidence we've gathered, is the work we've done sufficient that we're going to meet our reliability goals, that customers are going to be happy with the final product? And this answering all of these questions certainly takes a lot of effort and a lot of work. And what I'm going to suggest is that it doesn't always require testing, or if the testing you're doing should actually try to answer these questions, or the ones that you are actually receiving. And so I'm laying out a couple of different things here, and mostly about these kinds of questions, but let me ask you to join me in the chat window. And why else do you test reliability? What are some of the reasons that you run into that you end up heading to the lab or to the bench to do some reliability testing? What are the types of questions that you receive? And for those that are new to the webinars here today, that we generally ask a lot of questions, so get familiar with the chat window. So confidence in the design, it's kind of, are we sure? I agree, Thomas, that looks good. Abhijit, I'm not sure if I'm pronouncing that right, I'm sorry, but yeah, customers are saying, hey, this is what I want, and making sure that the design or the process you set up meets what the customers want. And sometimes it's very explicit. They may ask for specific activities. That comes along, certainly. And the question of how long will it last? Is it durable? Is it going to meet our warranty requirements? Is it going to meet our customer life expectations? Those kinds of things. Certainly, Paul, that certainly comes up. And then sometimes we share those test results with customers. And I'm sure that many of you have called a supplier or a vendor and asked for test information. about the materials or components or subsystems you were buying in order to understand, to some extent, if it's possible, just how reliable something is. And so there's verification, validation, there's confidence, there's meeting contractual obligations, and there's many, many different reasons we go into to the lab to do testing. And I don't think any of that's going to change. But I look at it as that through the product development cycle, what we're doing oftentimes is, especially with testing, but also without testing, is we're providing feedback to the system. We're helping to inform the organization, the rest of our team basically, how good is the product and where are the risks. And so it's a form of reflection back to the team concerning the design or to the process that we're setting up is, are we there yet or not? And so as a quick aside, I had to put in some of the red hearts there on one of the photos because here in the US anyway, it's Valentine's Day. So I wanted to, I saw a couple of those and figured I better add those in there. But there's many different stages to a product life cycle. And it's rare that we have the ability to conduct any significant reliability testing in a more formal way of determining if the product good enough or not during the concept phase. The concept phase, the product may and very likely doesn't exist yet. We may be simply the back of an envelope or some sketches or basic drawings, or here's the basic ideas that we're considering. It's really more in the concept or feasibility stage. Yet the feedback that we provide here is not necessarily directly reliability testing. And this one should be pretty obvious, is oftentimes, since we don't have prototypes or anything to really work on, we're probably not doing any real product level testing. Yet we do FMEAs and other hazards or risk assessments, and that provides feedback to the team. And some of that information is obviously based on prior testing, prior work that we've done, prior field data that we have. We also start looking at, well, what's the environment and how is a customer going to use this product? And those things then really start to help us to understand, is this design appropriate or not? Is the basic set of decisions that we're making at this point, will they work in the environment, and will they work as the customer expects to use it? And if those things aren't available in the design or in the concept phase, it really doesn't make sense to do much of any testing anyway, because we need to understand where we're going to use the product, what stresses, what customers are going to do to the product, how often they're going to use something, and so on, so we can design and build an appropriate test. The other part here is we start asking the question, are the reliability goals correct? And that's a reflection of what the customer expects, but also what material sets are we using. So even without testing, we can tell that if we want a 30-year product, and it's an outdoor application, say a solar panel, and we're using soft materials that are prone to UV degradation and oxidation, melt in water exposure, well, we don't need to do a whole lot of testing to figure out that that's probably not going to work. So if we want to make a product that's not durable outdoors for an application where we are outdoors, we may have to do some testing to prove to the people that believe they can do that is correct, but oftentimes it doesn't take that, just basic material properties and engineering. That's kind of a silly example, but the idea is that as we're providing feedback, we're also looking for and prioritizing what are those areas where the biggest risks are. Where are the areas that we're going to be concerned about how this design actually works? All right, so in your world, in how you work, in the concept phase, or as early in the program as you can get, how do you, without testing, how do you influence reliability? How do you help the team achieve or get on the right track in order to achieve their reliability targets. I see a couple of people setting up good goals, setting SMART goals, SMART being specific, measurable, I forget what the A stands for, realistic, and I forget what the T stands for. Robert, if you know the acronym SMART, what they all stand for, throw that in there. Yeah, lessons learned, Scott. Excellent. It's one of them that we can say, let's not make the same mistakes again. It's also, here's an area we can use to bound the upcoming design. Consider the risks, the FMEA and lessons learned, those all play a role in that. Previous experience, clear specs. Yeah, it's a combination of setting goals and also what do we already know. But in this entire process is also starting to lay out what are the boundaries of where we have the most risks. And this is really setting the stage for the ability to do meaningful testing later in the program. A couple other people are typing there. Hold for a second. There it is. Specific, measurable, achievable, realistic, time-based. Excellent. Thanks, Randall and Robert. I see realistic and testable, time-based. Well, as with all acronyms, I'm sure there's more than one way to do it, so thanks. But yeah, in the concept phase is we start that discussion, and it's also providing feedback early enough in the program such that we are already avoiding doing testing. If our entire program is to wait until we have something to test, we're missing a significant opportunity to actually guide or influence the design on its path towards achieving the reliability objectives. Now, throughout the development process, in the design and development process, includes industrial design, electrical, mechanical, software, all of the different engineering activities that go into creating a product. The number of decisions is amazing. So we get involved as reliability professionals. We often get involved with major decisions. Is this a new package or a new attachment method or something that is deemed pretty obviously as a high risk, and we may get involved pretty early with that. Or if something is causing a significant amount of concern or risk, we may get involved with that. But keep in mind that of the dozen or so, or maybe 100 different specific decisions that we get involved with, there's orders of magnitude more decisions being made pretty much every day as to which component do I put in this place, what material set do I use, what material stack up am I going to use, what set of coatings, what processes are we going to use. And all of those decisions are without our direct involvement. Now, we may be aware of many of those or some of those, yet we're not in the heads of the designers that are making these decisions. And so a big part of our work is not waiting to give them test feedback that their decisions are good or not, and the likelihood that we can actually test every single one of those decisions is very, very unlikely. But what we can do is start to continue in what I was talking about in the concept phase, is then set up those guidelines, the lessons learned fed information about what types of material sets. It's keep out regions on circuit boards to prevent cracking, for example, and fracture of solder joints. Setting up guidelines that are framing the sets of decisions that the design team needs to make. And that way, if it's bending the guidelines at all, that's a trigger then to have that discussion about what are the risks. If I need to uprate a component, for example, or push it closer to its maximum levels, well, what's the risk? What's the ability for us to understand that so we can make a coherent decision? Now, many times we're using different sets of models and simulations in order to allow our team to make those decisions, to compare the options that they have available. In electrical engineering, we have the ability of SPICE models, which allow electrical engineers to evaluate the performance of an electrical circuit. And it does some of the circuit analysis automatically for them and lets them compare lots of different situations or conditions. But it's also able to look at, are we derating it correctly? Are we designing enough margin into it? What if we push the voltage high or low? So we can simulate a voltage margining test on the performance of a circuit. Now this becomes trickier and you need more sophisticated models with high-speed circuits, for example. But many of those tools exist. And in the mechanical world, we have finite element analysis, oftentimes built right into the design packages. SolidWorks and others packages have basic capability to do finite element analysis. And so instead of just looking for where's the stress concentration or is this load adequate for the materials we're putting in, is also look at what's the variability of that assembly process or of that material set, and how does that impact the reliability of what we're doing. And so between models and simulations, with an eye towards how it affects reliability, we can start influencing or allow our design teams to understand and incorporate reliability into their decision making. And it's a matter of encouraging that behavior, encouraging that use of these models and making these decisions that way. But what it does is it also allows us to figure out, well, what areas do I really need testing for? Instead of trying to test every single permutation of all of the different ways that we're making decisions between vendors, between materials, between processes, is using a structured approach in that decision-making process to consider reliability and looking for those areas in, I don't think I have a graph here, but the stress strength curves. What we're looking for are the ones that are overlapping. So if we know that we have a flange that we expect quite a bit of stress on it, and in some cases it won't hold, well, what if we use some of the simulation tools and use a different material or different design such that the stress is well below where the strength is, and this upper part being the strength. And in this case, I'm just using a simple example of like a flange that's mounting some other load onto it. We don't need to test that to failure or even test it to determine whether or not we have a risk there or not. If we're close, many times designers will tell you, we're not real sure about this one, we're waiting for tests to do that. Well, it's a perfect opportunity to say, well, can we simulate it? Or can we build a mock-up of it as opposed to waiting, as opposed to simply waiting? And so that's the basic concept there. All right, so in the development phase, what can you do? Because I mentioned a couple of things in modeling and simulation, and there's also the design FMEA. But what can we do before we get prototypes at this stage to provide feedback? What are some of the tips or tricks that you're using while you're waiting for prototypes to show up that you can provide feedback to the team? Earlier, we've set goals. We've probably done some apportionment and some system-level modeling. There's a system-level FMEA. I mentioned the design FMEA. Yeah, getting it into the design reviews. Yeah, good one, Robert. And I'm assuming you mean not the ones that are the big death by PowerPoint meeting with the whole team, but rather the engineer-to-engineer type pieces of it. Proof of principles on models. I'm not sure what you mean, Thomas. What goes into that? Yeah, developing the block diagrams. Some people use fault tree analysis. Lewis, good idea. Yep. All right, thanks, Robert. Yeah, so it's that it might be a small team that you're doing those design reviews with, including the FMEA type work. Yeah, bringing in the historical information, looking at past failures and so on, the field history and what we know and don't know. As many of you knows, our designs are often evolutionary, and so many parts of our design may be identical or very similar to past products. Well, if they're working well in the field, it lessens the priority to do much of anything to improve it or change it, and thus reducing the risk that it fails. Now, be aware that there is some diligence that's needed to make sure that you're not creeping past some margin that was remaining in the previous product. It might be using, say, just a couple watts more power, but is that enough to cause problems with your power supply? And so it's doing some of that work to make sure that you don't cross any thresholds that would lead into problems. Yeah. In simulations, Anastasia is exactly right. At this stage, as the design takes shape, we can start using a lot of our physics of failure type tools and evaluations of everything from solder joints to how the circuit board will react given the voltage and margining and loading that it'll see for cathode anode filament growth, for example, within the FR4. But we can start evaluating the presence or the risk of the various types of expected failure mechanisms. And we can start, and this starts building on what we know about the customer and the environment, the stresses that it has, and how our systems will respond or react to those. All good stuff. Now, a big part of many of our designs is our supply chain. And so one of the things that we run into is that some of our suppliers, rightly or wrongly, may only rely on testing to the extent that they might be testing in reliability or trying to test in reliability. So if you're talking to a supplier that is either new to your program or you don't have much track record with them, and you ask them about their reliability program, and the first thing they tell you is that we do 100% testing. Well, sure, measuring the resistance of resistors is fine, and you can do that. How does that relate to the reliability part of what you're doing? What are you measuring that relates to, will it last for 10 years or not? Oops, that didn't work. I was trying to draw a question mark. So instead of asking, how reliable is your product, and they'll probably just point you to a data sheet, is ask them, how do you know your product is reliable? So as you're working with suppliers, and I think we've done a webinar or two, and certainly a bunch of podcasts on how to work with your suppliers in order to understand how well they understand the reliability of their product. And then more so is working with them is you can understand how to interpret their testing for your application. And that's, I think, the mark of really, really good suppliers. If they've got the models of their dominant failure mechanisms that are flexible to giving them the answers based on your set of conditions. So instead of generic, it passes some standard for 100 hours of testing at some set of conditions, they instead have, here's the Weibull distribution for time to failure, and it's dependent on temperature. And so that curve will shift depending on your application, and then they help you understand that relationship and why that actually occurs. That's way more informative than saying, oh, we tested a few of them, or we tested all of them, and therefore they must work. Ask the right questions for how do they know, what's the evidence, is a whole lot more meaningful. And so the other part here is with the supply chain is what do we know and don't know? So that continuation of the FMEA and hazards analysis type work is then a method to feed into, well, what parts of their process do we need to understand and control? Now, ideally, we don't want to test in reliability. We want to monitor the processes that impact reliability. So for an example, on a multi-layer ceramic capacitor, I'm going to draw just a very crude cross-section here with the inner layers of a capacitor, is in between these layers is a bit of a ceramic. In the ceramic layer, the thickness of it and the lack of defects in it create the capacitance for your circuit, for the electronics. Capacitor symbol here. And if those things are not cured correctly, and I'm using this as an example to the level of detail that you need to have for areas of high concern or risk for the reliability of your product. Now, multi-layer ceramic capacitors are often not considered a risky component. Yet, I was talking to the folks at CALS and at DFR Solutions some years ago, and they've done tons of different failure analysis of field failures. And I've also confirmed this with other test labs on looking at different products coming back from the field. Is capacitors account for a significant number, like a 30 to 50% of field failures. Now, even though they're discrete, simple, fairly inexpensive components, they do lead to a significant number of failures. Well, one of the things we've learned is that if you don't cure that ceramic correctly, it makes it more susceptible to cracking and failing. And so a modest board flex or an assembly step or a thermal strike to the product, when it's made correctly, would be immune to it, basically. But sometimes it may cause a failure. So it's looking down at if capacitors are an issue for you, or a risk, or deemed something that's important to not have cracking on it, part of it is understanding all the way back to the curing process of that assembly of that component. And then it's, do you have good process control on that? Is that process capable? Now, you could be looking at materials, say an aluminum extrusion, and how consistent is it, and how free of defects is it? How stable is that process? Or it could be electromechanical or software-wise or whatever, but it's getting down to that level of detail on your supplier, and many times your supplier's supplier, to make sure that it's minimizing the risk to the eventual reliability of your program. And you're right, Robert, it's really looking down at that driver of the failure, wherever it exists, and making sure that you can put it all together. This starts to build that lessons learned type portfolio, but it's worth the effort to guard that on occasion so that you don't cross those thresholds and violate your own guidelines. And so as you're going through the design process and working through your with suppliers or others, what are those red flags that indicate you need to pay attention to it? And I know that for me, it's often a new vendor. But what other signals do you look for that it's worth asking some more questions about or understanding in more detail? And so we may start getting some mock-ups, some breadboard designs, some early prototypes at this stage. Yeah, I'm seeing new design, new application, both good flags. New application would be, what's the set of stresses? How does that change? Customers are being more and more clever these days at moving into new environments and taking your products along with them. What other indicators do you look for? What other triggers? Yeah, cost reduction. Yeah, good one, Hernando. Yeah. Oftentimes, you can get this sense of false cost reduction. We can save a few cents on a component and pay more in warranty later. If that group is not considering the life cycle costs, it may or may not be a true root cause or a cost reduction. sometimes they don't like to hear about the life cycle cost. Yeah, pretty much anything new or different. Now, if you're in a development process, there's going to be a lot that's new and different. So those FMEAs and risk analysis type work, looking at stress strength considerations, uh, all start to play a role in understanding what do we need to evaluate. All right, so here's a completely different question for you. When is it too late to do reliability testing? You know, if somebody comes to you and says, hey, we need to do reliability testing, is there a situation when you would say, no, it's too late? It doesn't make sense to do the testing now because it's too late. Yeah, when the design is frozen. Yeah, I agree. It's, if we're not going to do anything with the results of the testing, then why are we doing it? Now, there's some argument there that's to do it anyway, but I still argue that it's oftentimes it's not really useful at that point. Yeah. Now, future iterations could be used for that, and we could start that off cycle. It gets tricky is will this project pay for testing that will only be useful for the next project? Oftentimes, that cost will be rolled into the cost of the current product, and that's a tricky discussion to have. And making sure that it goes out to the bigger picture for the long term, that makes a whole lot more sense. See a few more typing here, so hold on for a second. It's never too late. You always learn something. I don't know, Thomas. Yeah, it is better earlier. So, and so Abhijit, you mentioned that after lockdown. So if the design is frozen and the team is not going to change the design, I think there's very limited value in the testing because it's only really going to be of use to make any changes or help them make any decisions if you find some major problem. I think I remember some Dilbert cartoons where the product testing showed that the product exploded and sent spikes throughout the room or something like that. And I think they were even at that point going, maybe we should redesign it. Uh, it's kind of that situation where if you're pretty much locked down, you're only looking for major safety issues at that point. And it still has some value, I'd imagine. Yet, in order to meet your reliability goals, you really get blocked out of much value. And also, another form of that is when the cost of making changes it affects what your ability to actually um, implement any changes. The later you go into the program, the more components and materials and processes are set up to move your product along the life cycle. And so implementing a change as you head into production is a whole lot more expensive than it is when you're in concept phase and early design phase. And then the third category I'm going to mention here is that if you're going to do a test and it has, say, a 20% confidence because you're only using 3 samples of at least a 50% reliability over 5 years, well, are we really learning anything with that? If we get a failure, it's going to be a major issue, which arguably could be of value to know that. Yet, it's not really going to help us understand are we there yet or not. Any of those questions that we typically get asked, is it good enough? Is it the right choice? Or is it going to last long enough? If we run so few samples under such a benign set of conditions that we get very little information about its 30-year life or even its 1-month life capability of being installed, what is it we're really learning? Are we really added any value to the discussion rather than, oh, it passed, but it doesn't really mean anything because we could have put a couple of bricks in the chamber and it would have been just as meaningful. I actually used that in a discussion one time and they looked at me strange and I said, if the results of your test actually do not inform you one way or the other, what was the purpose of the testing other than to consume some electricity for a chamber? So reliability really does need to add value, reliability testing that is. And so the real connection here is that we can discover failures that we didn't know about before. And so this concept of discovery, of halt testing, of testing to margin, testing to failures. If we take 3 samples and we run them under use conditions for a few hours, we might learn something about functional performance and timing and some of the other aspects of how the software actually works or how the system performs when first started up. And to some extent, that's a test. But it's unlikely by the time we get it in the reliability world that that's going to result in any significant, in any failures whatsoever. If we do, it's worth reporting back to the appropriate teams to fix that. But if we're only testing, say, 5 or 6 samples, and the question is, will it last long enough? Will it last 30 years as a solar field installation or 2 years as a cell phone? If we test a couple of them, just power them up, play with them a little bit, power them down, we haven't really learned anything and haven't provided anything of use. If we take it to failure, well, how many drops of a cell phone causes a failure? And what kind of stress or forces does it take to crack the screen, for example? Now we're creating failures and information about how that mechanism occurs. Now that's useful. Another one is that we reduce uncertainty. We may have a pretty uncertain understanding of, say, a failure mechanism. So will we get tin whiskers in this current design? Now, as far as I know, we don't have a perfect test to determine whether tin whiskers will happen or not. There's a number of design guides and other aspects that we can use to avoid that. But there are a handful of tests that, if tin whiskers are going to occur, the set of conditions for these environmental tests will promote the growth of tin whiskers. And so it gives us a little bit more information of reducing the uncertainty around that question. Now, it's marginal amount of return on investment, marginal amount of value, but in some cases, if we can say we're at least 10 years reliable with some probability, that's better than not knowing or having our previous information only good out to 5 years, for example. And so by reducing the uncertainty or bounding the questions that we're trying to answer a little bit more precisely is another way we can add value with our testing. And the other one is often what we consider with reliability testing, will it last 5 years? With how many failures do we expect? How many spares are we going to need for a 10-year life of this product? Or will this fleet survive, say, 100,000 miles for each vehicle with some probability? And some of our testing can help us understand that and actually make reasonable estimates for that. I saw Kirk on the line. You're probably bristling at this part of it, but in some applications, Kirk, not just we do need to answer that question. And so, yeah, it is. I did mention that we do need to run to failures, and in estimating reliability, it's often prudent to run to failures, making sure that we get the right failure mechanism excited in our testing. And so there are ways that testing can actually add value. It's a matter of making sure that when you set up the test that you're considering exactly what source of value you're going to be in there. All right, thanks, Kirk. And so we talked a little bit earlier about the number of different things you can do instead of testing. The simulations and using lessons learned, previous product field testing, or field returns and the root cause analysis for that. But we can also, instead of testing an entire prototype, there's a number of things we can do. And let me see if I got, yeah. And so I'm going to mention a couple of things here, is that instead of testing the entire product, which often is late in the development cycle before we get our hands on full products or even significant portions of products, there's a few things we can do. And we mentioned already models using past field data, but then I don't know that we've talked about characterization, and I'll expand that here briefly in a minute. So what else? What other ways could we avoid doing, say, system level or product level reliability testing? Or is this pretty much cover up? And so models, right? In literature, we've got tons of different articles written. Just last month, I was at the RAMS conference, and a number of discussions were about evaluations and testing that was done to evaluate how things failed, understanding different failure mechanisms. Different conferences, well, there's a prognostic health management conferences. There's a number of different component level or material level conferences and sources of papers that talk about very specific failure mechanisms. And it's those mechanisms and the models associated with them that allow us to, as a minimum, frame the testing we're going to do. But more importantly, is they allow us to prioritize which areas we want to do testing. So if we've got decent physics of failure models, and it allows us to understand where the risks are, where we need to go actually do some physical testing to bound it for the difference between the models and our physical product. Instead of testing every single variant of your product and its design and the various components and so on, is using SPICE models and physics of failure models and finite element models. We can hone in or focus on the very specific areas where there's the most uncertainty or the most unknown. And it allows us then to prioritize where we put those precious few samples that we have. Now, another way to do this is using literature search and empirical models that exist in the literature or in many of our textbooks, is to frame out where we're going. So empirical models would be like the Coughlin-Manson equation. And so if we know that we've got a wear or a metal fatigue situation, we may be able to find those models of use to help us frame the amount of uncertainty that we have concerning this particular setup. And so failure models are pretty handy. They also are pretty useful as the first step for designing any test and understanding the failures that you do see as to characterizing what kind of risk you're actually facing. So a lot of what we deal with is dealing with failure, but more importantly, it's dealing with how the failure will manifest itself over time, under what conditions. But let me ask this question. I'm sure many of you have used different reliability models at times. What assumptions are problematic? Yeah, and I was just thinking of you, Kirk. You're going to jump in there with the activation energy, which I can say faster than you can type, but maybe something else. What assumptions, as you're using models, are something that you really should go out and check? Constant failure rate. Yeah, John, excellent. Yeah, as many of you know, I have a website called knowmtbf.com, which kind of goes at the heart of that assumption. It's convenient to assume that you have a constant failure rate or you're in the flat part of the curve. It makes testing a whole lot easier. Yet, it's very, very, very rare that it actually exists. Even if you have multiple failure mechanisms, all with betas greater than 2, by having that mixture of failures, it tends to reduce your overall system beta value, and it can get closer to 1. But individually, the failure mechanisms are anything but 1. And so setting up a test assuming a constant failure rate tends to ignore or avoid the ability to see those failures. The test would run a whole lot shorter. Yeah, and Gene, you're exactly right. Sometimes customers use our product in slightly different ways. So one of the assumptions is that we know how the customer is going to use the product or what environment they're going to use it in. We need to add that variability into the system, into our evaluation of where the risks are. Yeah, acceleration models, they all have uh, assumptions. And you're exactly right, Andre. And a good number of the models assume that you're going to have that the failure mechanisms are relatively independent of everything else that's going on in the product. So as a power supply starts to fail, it may start to heat up and create more heat for the rest of the components. And that increased amount of heat may excite, say, metal diffusion type problems. And as that diffusion occurs, it may continue to heat up. And I'm avoiding the battery analogy, but you can get into a situation where a sequence of events unrelated to your particular area that you're testing can really muddle and create a runaway situation, which changes the nature of the rate of failures. And so assuming that you're going to have a well-defined characteristic time to failure model is hazardous, and it's worth checking and seeing how the interactions within your system could cause that model to change significantly. Now that's hard to do. It's not a trivial task to take on, yet it's worth checking whether you're dealing with activation energies or you're dealing with an acceleration model or you're dealing with how a customer uses and so on. Is each one of your tests is going to come with a whole bevy of assumptions. And you won't be able to test every single one of them, but at least acknowledge they exist. And for the ones that can significantly change the outcome, those are the ones that are worth checking. Another whole area that we deal with is field data analysis. Now the issue with this is that it's the last product, and you may be in an environment where it's a new team and they're assembled to create a new product, say a new platform. It's still similar to some of the previous ones, yet it's this not invented here syndrome. Well, that was the last product. We've learned a lot, and so we're going to do it better this time. But there's still, I argue, and I think I saw it I saw it a couple of times in the comments, is that what we did in the past can often provide a tremendous amount of value to our program, and it helps us, one, avoid testing. But it does require that we gather the right information, and including how it was used, what environment it was in as much as possible, a detailed root cause analysis. You know, telling a designer to make a product better, we want it to fail less often than the last one, is a noble goal for the new design team. Yet, any designer engineering team I've worked with is they come back immediately and says, well, what was the problem last time? What were the things that failed? And so this takes a little bit of forethought as you launch products is, well, how are you going to collect that information? One, so you can respond immediately to your current situation, but more that you can build that set of lessons learned and information that you can use on the next system. So field data is noisy. I don't think any of us have perfect field data. What are some of the steps you can take or have taken to get better field data? I just noticed in this picture in the lower left-hand corner, it looks like a high-tension power line is going by there. That might be worth some field data for these guys is to make sure they have enough clearance from the high-tension lines. Yeah, fracas and logging systems. This generally assumes that you have some way of tracking when the product was made. Serial numbers is the old-fashioned way, but oftentimes we have an electronic or a scannable type label on a system that allows us to gather its history pretty quickly. One that I ran into is that we changed the call center. For this was more of a consumer product, high volume product, is in the first couple months of production, of shipping the product, we changed the call center tree, action tree, of decision tree basically, such that we got a higher percentage of units were shipped back. We sent them a replacement and said, box up one you have and send it to us. And then they gathered a bit more information about the conditions for that product and where and how it was used, what they saw. Just that little extra effort for a couple of months was about all we could get through with the call center team and the field service teams and their budgets. The value to them was that it would reduce the load quicker if we got better information on what was failing, and if we got more units back that we could do failure analysis. Now, on the engineering side, is we devoted a team to dealing just with those returns. And they were from the development team, and they were kept on, rather than assigned to a new product, they followed the product and for a couple of months and had a pretty much a fast track to implementing changes. But it allowed us to do two things. One is improve the current product, but two, it allowed us to justify that tracking field information and getting better sets of information about how it's used, where it's used, when it's installed, all of those bits of information allowed us to make much better models for future products, better understanding of its current field situation, along with just improving the current one. Yeah, the recalled parts. I worked with one group that they did 100% detailed failure analysis on their field returns. And it was expensive, yet the program deemed it essential for them to not miss a unique new failure mechanism. And so a lot of it was step and repeat. They saw a lot of the same things. So part of the difficulty was getting the technicians to be aware of something different or new. And so that was a challenge in and of itself. But it created a lot of wonderful information that allowed the design team to continue to evolve the product. The other part we can do is characterization. Now here it's really focused on those failure mechanisms. And I mentioned the ceramic capacitors earlier. If we're going to say use a new process to cure the ceramic on these capacitors, well, one, we might not know what the new failure mechanisms are or if they are the same. And so it'd be working on a set of experiments and characterization work to fully vet that new process such that we could build the failure models. We could build the physics of failure type models to help us understand it. But oftentimes these are the experiments, and it's really an experimental work, often in parallel to the development work, so that we can fully understand the interactions, the behavior over time, the response to the various stresses that we expect. And it allows us then to evaluate and explain, provide feedback basically to the team. Are we on track or not from that evaluation? All right, so it looks like I'm a little bit short of time, but I'm going to leave this question to you as a thought experiment. Let's say you're taking on ballooning and you're designing a new rope to hold your basket to the balloon. Now, how would you go about testing that? You know, tensile strength is important, but it's obviously not the only one. So I'll leave that as a quiz for you. So when should you do reliability testing? Well, when it adds value, when it actually is linked to a decision, and when it actually provides information. If it's just going to check off a list at the end of the day, and nobody's going to use it to make any decisions or evaluate it or look at it, well, then the argument is, well, why are you doing the test? So as you set up tests, is making sure that the test actually is going to be useful. It's going to save somebody time. It's going to materially reduce risk for a future decision problem, or say halt test, it helps us to identify weaknesses in the design that then we could prioritize to improve the product. But we also have questions of some of these standard tests that we run. I struggle with some of these, or many of them, as to how can testing 7 samples for 100 hours under 85C really provide any value to us? And for years, we've never had a failure in that test. Well, what is that really telling us, or what is it really evaluating? What does it really mean? The other part here is it really needs to be connected to a decision. So as you start setting up testing, it's not enough just because somebody said, hey, go run this test. Now, I caveat that on if the customer is paying for it and wants you to do it and it's a condition of the sale, well, then we're kind of boxed in. We're going to have to do that test. Now, we have the opportunity to improve it so that it actually does add value. But as a minimum, you need to check, well, who needs this information by when and to what degree, what's useful for them as a result of this test? What are they looking for? If you go off and do halt testing, but they wanted to know what's the probability of surviving for 20 years, well, we missed something right up at the start. We need to design the test to answer the questions that are at stake for decision making. And so it's, if there's nobody is going to make a decision based on the data, you know, why are we doing the test? And finally, it provides information. Is in many cases that our testing is going to tell us about the time to failure behavior of a specific failure mechanism, or it's going to confirm models that we used earlier are correct. Kirk, you mentioned activation energy. We may make an assumption over a range. It might be of 0.5 to 0.7 electron volts. But in testing, we could take steps to verify what is our actual activation energy and then adjust our models accordingly. And so breaking wings on aircraft, that's often very well modeled, and the one test they do is really aimed at verifying model assumptions and parameters, and so on. So the test has got to result in more than we ran the test kind of report. It really should result in what failed, what are the failure mechanisms, what's some tangible information, not a pass-fail, but some real information that our team can use to make decisions. Now, there's a lot of useful stuff we can get from testing. It just takes some forethought to make sure that when we set up and run testing, that we're getting a lot of value out of it. And so, I went a little too far there. Look at the suite of testing that you're doing, and for some reason that's not going to stay there. So take a look at every test that you have in your program, and can you answer those questions? Does it add value? Is it provide information? And for whatever reason this is, and will it inform your decision makers? I think I set a timer on that one for some reason, but it only lasts for a few seconds. So the whole concept here is that if the test is not going to make a difference, I strongly argue you should not do the test. If it's going to add value, then make sure that the test actually is designed and executed such that it provides the value promised. And that's the bottom line for me. And so here's the final slide. I'll stay online. There's the slides over on the right side. I believe they're available to download. If you have trouble with that, let me know. A handful of other links. You can track down some more information. And let's see, I'm seeing Kirk, you added the quote from Packard: reliability cannot be achieved by adhering to detailed specification, formula, or analysis. Some of these may work. Let's see, I'm paraphrasing a little bit. But there's only one road to reliability. Build it, test it, and fix it. And it's the build, test, fix that was built right into a lot of the life cycles that we deal with today. And repeat it, repeat it, repeat it till you get it right. And I think Greg Hobbs would also argue that this build, test, fix, and find the weaknesses, make it more robust, really does make sense. As our products and timelines get tighter, products get more complex, it's just not possible to build, test, fix to everything that we need to before we launch. The risks are just too high. So understanding and prioritizing and focusing on what you know and don't know is a great way to get way more value out of the testing that you're doing. So not to contradict what Packard's and Hobbs and others have said in the past, I think there's still a role for testing. The danger is that if the testing is not actually serving you and your decision makers, then I think we're not really doing build, test, fix. So, and I'm drawing a complete blank at what the webinar is for next month. I think I have one on the schedule already, but I'm working on a few more for, I think, April, May, and June. If there's any ideas or suggestions, let me know. Look forward to hearing from you on that. And thanks for everybody for attending and participating in the chat window. That's all good stuff. And I'm going to end the recording here, but and say thanks one more time. But I'll stay on.